Hey everyone, today we're talking about sequences. It's a whole new idea that we haven't previously seen. And the sequence is very simple. It's just an ordered list of real numbers. There we go. And I'll give you an example. I'm always going to draw sequences. This is a bit different from the book, but I'm always going to draw the sequences in a bunch of curly brackets. So, oops, that's not meant to be a 4. I was going to put a 5 there. So our sequences are literally just an ordered list of real numbers. This is the first one, the second one, the third one, the fourth one. And I'm often going to use the notation where I represent the general term, and that's meant to be a nice curly brace. I'm going to use the general term a sub n. So here, a sub n is just, well, the nth integer, right? A sub n here is equal to n, because I'm going to sometimes write this starting at n equals 1. And this just means my sequence starts at n equals 1. In other words, I'm going to take my a sub n, it's just n, I plug in 1, I plug in 2, I plug in 3, I plug in all of the integers. So this is a sequence, right? It's just literally a list of numbers, but I'm going to donate it as this a sub n, denote it as this a sub n inside the brackets, where a sub n is just the general term here. So here's the definition from the book. A sequence, see exactly what I've written. They don't usually write the n there. If you don't see anything written here, it's assumed to just start at 1. So normally when you see this, n is bigger than or equal to 1 and n's an integer, and we call that number the index. So what we get out of this sequence, if you think of the example I've got over here, the first term was 1. There's the first term. The second term was 2. The third term was 3. There's the third term. The fourth term was 4. And that's why I then concluded that the nth term is n. Okay? So these individual things are terms in the sequence. These numbers are terms. Each of these is a term in the sequence, if you can see that color. N is the index for each term, and then we essentially get a list of numbers that are ordered. And we can start at different values of n. It doesn't have to start at 1. If I don't tell you otherwise, we usually assume it starts at 1. But that's pretty much it. Sequences aren't very complicated. They're just a list of numbers in a specific order. That's what I mean by an ordered list. These numbers are given in a specific order. So let's have a look at a few examples. So here's the example of a sequence. If you excuse my horrible curly braces on the ends there, the sequence is just this ordered list of number, right? A sequence, just colloquially, a sequence means a bunch of things that happen one after another. And that's what we've got going on here. We've got a bunch of numbers happening one after another. So what's the general term in this case? The general term, well, looking at this, the sequence that we're looking at are just the odd numbers. So one way to represent that would be 2n minus 1, starting at, well, if I start with n equals 1, plugging n equals 1 in here produces 1. So this formula would produce all the terms in that sequence. But it's not always unique, because another way to write it would be, for example, 2n plus 1. And we could start with n greater than or equal to 0, because when n is 0 we get 1, when n is 1 we get 3, when n is 2 we get 5, and so on. There's different ways to represent the general term. For example, I could write it as a sub n is 2n plus 5. And then if I started with n, I think starting at minus 2, then a sub minus 2, that would be the first term coming out of this, would be, 2 lots of minus 2 plus 5, well, that's 1. And then a sub minus 1 is 2 lots of minus 1, plus 5, which is 3. And then a sub 0 is 2 lots of 0 plus 5, which is 5, and so on. And so you see that this generates the same sequence as each of the formulas. Each of these is a different way of representing the general term, right? I could do it with the purple one, I could do it with the green one, but each of these produces a different formula, but the underlying sequence is the same in each case, and that's the important thing. So this is just a sequence which I could write as, just using the one at the top, the simplest one, I could just write it like that. Right? And without putting anything there, I'm assuming n starts with 1, or I could just explicitly say n starts at 1. And then n's an integer. So n is an integer, we call it the index, and we just start with 1 and then we increase. Down here we start with 0 and increase. This one starts at minus 2 and increases. Let's have a look at another example for these things. Here's a sequence that I could think of as, well, the general term in this case might be 1 over n plus 1, where I would start with n equals 1, right? Because when n equals 1, I get a half. When n equals 2, I get a third, and so on. So this is 1 over 1 plus 1, which is 1 half. And then the second term is 1 over 2 plus 1. That's 1 third. You see how this thing is working? This is going to be 1 over 3 plus 1, and that's 1 quarter, and so on. So each of these is a sequence, and the sequence is just the ordered list. And what I'm trying to get at here is there's different ways to represent a sequence, but at the end of the day, the mathematical object is just that list of numbers, and it's the same in every case in that first example. And here's a perfectly good way to represent it in this example, but we might represent the general term differently. This sequence would also be equal to 1 over n, where we just start with n being 2. So here we'd say n is greater than or equal to 2. Right, or I usually just write equals. So n equals 2 is our starting point, because that produces 1 over 2 is the first term, and 1 over 3 is the second term. So just different ways of looking at the same sequence, the same list of numbers. So let's have a look at another example. And here's another example, and I haven't commented on so far, but those 3 dots mean that the sequence continues forever, following the pattern that's kind of established by the terms we can see here. And if you look at the terms you can see here, we can literally write them out and say, well, let's say A1 is minus 1, and A2 then would be 8. So the third term in the sequence would be minus 27, and the fourth term in the sequence would be 64, and the fifth term in the sequence would be minus 125. But we can do better than that, because I notice that 8 is 2 cubed, right? And 27 is 3 cubed. So this is 3 cubed, and this is 2 cubed, and this is 1 cubed. Well, that has a negative, and that has a positive, and that has a negative. So does this fit the pattern? 4 cubed, 4 fours are 16, times 4 is 64. So now that's positive 4 cubed, and this is indeed 5 cubed with a negative, and presumably the rest of the terms in the sequence follow that pattern as well. So what's the general term? Well, in this case, we can see that the thing we're cubing is equal to the value of n here. These values are the same. Right? The a sub 3 has 3 cubed. A sub 2 has 2 cubed. So the general term, a sub n, is going to be n cubed. That seems reasonable. Now, how do I deal with this? Well, there's a minus sign and then a positive, so it's got an alternating sign. So just imagine I put a minus 1 out the front. Well, that's going to make all of the terms negative. So I can make it alternate by raising that power to, I'm going to move the n cubed a little bit, I'm going to raise that minus 1 to the power of n. Because think about what that does. Minus 1 to the power of 1, that's minus 1. Minus 1 squared, well, that's 1. Sorry, that's a horrible 1. Minus 1 cubed, we're back to minus 1, because it's minus 1 cubed is this term times minus 1 again. And so this is an alternating list of 1s and minus 1s. I'm writing them really badly here. So this term here will reproduce the general terms, reproduce the terms we see over here. So here's the general term for the sequence. And we're going to get really used to kind of looking at this and coming up with a pattern. Whenever you see this alternating pattern, where the sign alternates, that's going to correspond to a minus 1 to the power of n, which kind of follows from the argument I made down here. So we'll have lots of practice looking at them. So let's have a look at another example. This time let's take a sequence and ask what happens to the terms in that sequence as the value of n gets large. In other words, as n goes to infinity. So if you think about the terms in this sequence, it doesn't say otherwise, so I'm assuming this starts at 1. So plugging in 1, I get 1 plus 1 over 1, which is 2. The next one, I plug in 2. Right? This is the n equals 1 term. And then the n equals 2 term, I'm going to get 3 over 2. And then each time, this is going to get 1 bigger on the top, so 4, but 1 bigger on the bottom, over 3. 5 over 4. 6 over, what is this? 4. This will be a 5. And then 7 over 6. And then 8 over 7, and then 9 over, I mean, you get the idea, right? Because each of these is getting bigger each time, 10, and this will go on forever. That's the idea of this sequence. These are infinite sequences in the sense that they go on forever. That's what the dots mean. So if you think about this number at the very beginning, the first term was 2. At this point, the term is, well, 11 over 10. That's 1.1. Right? And if I think about this, this is the number 1.25. These are numbers I can do easily in my head. The first term was 2. This is 1.25. This is already 1.1. What do we reckon's happening? Eventually we're going to get to a term like, we're just always going to have terms where the number on top is 1 bigger. So eventually we're going to get 101 over 100, which is 1.01. So if we look at the general term here, it's literally, we can just read it off, right? It's n plus 1 over n. And you've probably already seen it, that I can rearrange it like that. So what happens as n goes to infinity? Well, what happens to 1 over n as n goes to infinity? Well, we can plot these things. We know every single one of them is bigger than 1. So suppose this is the line 1. What I need to do is plot all of the values that I had here. So one of the values was 2. There we go. So when n equals 1, and I'm going to start marking the values of n along the axis down here. And the thing to remember here is I'm not going to draw a continuous graph. I'm not going to draw a continuous function because these aren't continuous values. It's a list of discrete numbers. And here I've drawn a few of them in. And what's happening is they're getting smaller, right? This is when n equals 4, we got 1.25, which is about there. It's a quarter of the way up. And then each of these is getting closer and closer to my badly drawn line where it's 1. And it looks something like this. So there's no curve joining those white dots. They're the values for the different values of n, right? That's a sub 1. That one's a sub 2. This one's a sub 3. These are discrete values, right? Discrete meaning they're not continuous. We just have values at each value of n. This is not a function of x. But we can kind of look at it and we can conclude that this thing looks a lot like the limit when n gets really large is going to be 1. Right? Because these white dots, each of the dots is getting closer and closer to 1. So it seems to make sense that there's a limit here. So let's unfurl a few of these ideas. In fact, you could say more. You could say it really makes sense that this is going to be the same as the limit of that thing. Well, I mean, it has to be. That's what that thing is, right? This is just our rearranging of a sub n. But now think about what we know about functions from Calc 1. Do we think that's going to be the same limit, or even from L'Hopital's and things in this course? So do we think these are equal? Right, this is something we know how to take the limit of. This is the limit of a continuous function. When I use x, I'm thinking about a continuous function, 1 plus 1 over x on x bigger than 0. I know how to take that limit. It makes sense that the limit for these discrete values are going to be the same. So I'm just going to show you a few theorems that in fact say that this is true. All right, so here's the definition, the formal definition of the limit of a series. We're going to use this nice notation just as we've done before. And if that limit exists, we're going to say that this sequence converges to the limit. Right? The sequence of numbers converges to a limit. So in the previous example, here we go, it seemed like the sequence here converges to 1. So the limit here was 1, and this is a convergent sequence. If it doesn't converge, if the limit diverges, if this limit does not exist, we say that that sequence diverges. And we use similar language for improper integrals, if you remember. And if it just keeps getting bigger and bigger and bigger, if the terms in the sequence keep getting bigger and bigger and bigger, for example, our first sequence here, these numbers just kept getting bigger and bigger and bigger. So this is a sequence that diverges, and more importantly, it diverges to infinity. So what does this all mean? Imagine I've got a sequence of values. Here's a sequence of values, right? And I'm only going to have values for this sequence at n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. You get the idea. So I'm going to have a discrete bunch of n values. And as I calculate these n values, I'm going to get values for the sequence, right? If I plug in the n values, I should say, I'm going to get values for the sequence. So a sequence is a bunch of numbers, and I'm just plotting those numbers along the y-axis here. So there is a sequence. This is a sub 1, this is a sub 2, this is a sub 3, and I'm just marking them on the y-axis. What this business says is that for every number you can name that's positive, so no matter what small number I name, let's suppose I name a number that's that big, then I can go that far either side of L. There's the top and there's the bottom. So this is L plus that number epsilon, and this is L minus that number epsilon, right? Just this is the value on the y-axis, so L plus a little bit and L minus a little bit. So I get to name that number, but no matter what number I name, no matter how small I make it, if I look in the region between L plus epsilon, this is an inequality. Think about what this inequality says. It says a sub n minus L is less than epsilon, but also greater than minus epsilon. If I remove the absolute value, this thing is the same as that line there. And another way of saying that is a sub n. If I add L to both sides, a sub n is between L minus epsilon and L plus epsilon. All I've done is add epsilon to both sides here. And you've seen this limit definition in Calc 1. But this idea says that the value of a sub n is between L minus epsilon and L plus epsilon. In other words, it's between these two lines that I've drawn here. As long as you get to some point, n, which is bigger than m. So if I name a point, if I call the point m, if I call it 4 in this example, then that point, that dot there is kind of in the wrong place, right? It should be a little over. Oops, I didn't move it very well. There we go. There's my dot. I'm doing a bad job. All right, so there's the dot. That's a sub 4, right? So notice that a sub 4, a sub 5, a sub 6, a sub 7, all of these numbers, all of these values are always between L minus epsilon and L plus epsilon. In other words, they satisfy that idea. Originally, at the beginning, the numbers aren't inside that little envelope. I'm thinking about a little envelope. If I'm going to claim that L is my limit, that's what I'm claiming. L is the limit. If I'm going to claim that L is the limit, then all the points should be within a small distance above and a small distance below that limit L. That's what this statement says in a mathematical way. But it doesn't have to be true all the time. It just has to be true eventually. And by eventually, I mean for all the values that are bigger than m. So in this case, for the picture I've drawn, as long as n is bigger than 4, that's our m, this inequality is true. In other words, this inequality is true. Now, how does that correspond to a limit? The key idea is back here, the fact that that epsilon is a positive number, but this has to be true for every possible positive number. So no matter how small I make that gap, I start at the limit L and I go up a little tiny bit and I go down a little tiny bit. No matter how small that epsilon is, I can still eventually find a place where all of the points lie close enough to L. So if instead of being the epsilon you see on the picture here, I shrink the epsilon down to between these blue lines, well, you see now, well, that one's not really in there, but once I get to there and onwards, all of the white lines are between the two blue lines. All right, so that's the idea. No matter how small I make the epsilon, I can always find some m. In this case, the m looks more like it would be about 7, right? In this case, for all the points at 7 and beyond, they will be in that interval. So as long as I can do that kind of thing, the limit exists. We saw a very similar definition for limits for functions that are continuous. We're not going to use this very much in its formal sense. You can see some examples in the book. The idea is that this limit exists, it's well defined, and it's very similar to what we saw for the limits of functions in Calc 1. So let's see how we might use it. Here's the first theorem in the book, and it's essentially what I said in the previous example. And it says that if you've got a sequence that's defined by a function, right? If this sequence is defined as the values of a function at a bunch of numbers n, then the limit of that sequence is going to equal the limit of the function, right? The function which we can use the sort of notations and the ideas we've had from calculus. And the idea here is that this sequence of numbers is generated by this formula where n is a discrete number, 1, 2, 3, 4, it's a counting number, it's an integer, positive integer. Whereas the x that's being used over here, this x is a continuous variable. So we can do things like apply L'Hopital's rule because we can differentiate. You can't differentiate, let's go back to a picture, you can't differentiate the points along here because it's not a continuous function. There's no curve, there's no slope, none of those things make sense. There's no curve passing through any of these points, so there's no way I can define a slope at that point. But if I can use the idea of this limit, then I can, because what we're doing is we're saying, okay, well this was actually, this sequence that I drew here, it was actually defined by this. It was defined by the function f of n equals n plus 1 over n, right? It was defined by a function. And if it was defined by a function, then I can draw that function through the points. Now the sequence itself is not the curve, it's the points. But I can draw that function. This red thing is the graph of f of x, where I'm kind of adding the x-axis along here. And it agrees with the values of the sequence at the integers, but the difference is that this nice curve has values at every value of x. This is 1 plus 1 over x, or put another way, it's x plus 1 over x. So this red curve is defined for all values of x. The sequence itself only has values at the integer points, and that's the difference we're looking at here. So here's an example of a sequence. Let's find the limit as n tends to infinity here. So this is literally going to be, we can write it out, just an infinitely long list of numbers. And a sub n here, the nth term in the sequence, is just given by that formula, right? And this is true for all n bigger than or equal to 1. And what we want to do is find that limit. So find the limit as n tends to infinity of that nth term. And what this theorem tells us is we can do that by noting that this is defined by the function f of n, where f of n is just n e to the minus n. And so I can think about the function f of x, which is x e to the minus x, right? And this might seem like I'm just playing a game, but this is a differentiable function, and this is a list of discrete values, right? This is just the terms in the sequence. And the difference is, this is just a formula that generates a list of numbers, whereas this thing down here is a function that's continuous on all real numbers, and so we can calculate that limit. And in this case, it's a fairly straightforward limit to calculate, as long as you remember what we did in an earlier section, because this thing is indeterminate. It's an indeterminate form of type infinity times 0, because remember e to the minus x looks like this as x goes to infinity. And x obviously goes to infinity as x goes to infinity. So I'm going to rewrite it as x over e to the x, just putting this in the denominator, and now this is an indeterminate form of type infinity over infinity. And remember, that's one of the things that we can use L'Hopital's rule for. So applying L'Hopital's rule here will give us 1 in the numerator and e to the x in the denominator, and e to the x is going to infinity, and so this overall limit goes to 0. So we now know that the sequence itself goes to 0. This list of numbers gets smaller and smaller and smaller as x gets larger and larger and larger. And we knew that by leaning on what we already know about functions, continuous functions and their limits. So that's the entire point of this theorem. We can use what we already know. And it's not just this theorem that follows a similar pattern to what we already know about limits. There's also a sequence of limit laws for sequences. And they behave very similarly to the limit laws we already have for functions that we know from Calc 1. So you can't really see that blue on there, or the green on there. But if I have two different sequences, so I literally have two sequences of numbers, which just means two lists of numbers that are in a given order, and we're interested in finding their limit. So we find that as we go along this list, the numbers in this list get closer and closer to L. That's what this limit means. And if we look at this list of the numbers B, as we go along that list, the numbers as we go along this list get closer and closer to the number M. Then I can add the lists, and when I do that, and by adding the lists, I mean adding them term-wise. So for example, let me rearrange a few things. what this kind of represents is they're saying, what's the limit as I add the terms? And we do it term-wise in the sense that we add the A's, we add the B's, we add the A1 and the B1, and the A2 and the B2, and the A3 and the B3, and the A4 and the B4. So there's the first term in this new sequence of A plus B. And there's the second term, and there's the third term. Well, these numbers should all get closer and closer to L plus M. And that's what this is telling us. If I multiply the terms, right, what that means in this case is that each term is multiplied by the corresponding term in the other sequence. So I take A1 and I multiply it by B1. I take A2, I multiply it by B2, and so on. Eventually they get closer and closer to L times M. I can take the ratios of terms. I can take the product of the terms by a constant, which literally means I'm taking the sequence and I'm multiplying every term in the sequence by C. In this last one, we're just taking the sequence that's C times A sub n, so CA1, CA2. Well, that's obviously going to get closer and closer to C times the limit of the original thing that we had, because these numbers were getting closer to L, those were getting closer to M. So this behaves very much like we would expect a sequence to be, function's limit to behave. So this is just a generalization of the kind of things we've talked about. We'll play with these. I'm going to put a bunch of these kind of problems on web work for you to practice with. It's mostly notation here, right? We're just dealing with a list of numbers, and it's mostly how we're denoting that list of numbers and what the symbols mean. That's what we're getting used to. Okay, so I think I'm going to leave that there for today. In the next video, we'll cover the rest of the material in this section, which is talking about how these sequences converge in a bit more detail. But we've got a good starting point. Have a go at some web work, have a go at the initial practice problem, and I'll talk to you soon. Come to office hours if you have questions.